Here's a chart from your textbook showing how we can classify materials. Over here we have the nonlinear materials referred to as ferromagnetics. These are materials that are strongly attracted to a magnet. Examples are iron, nickel, cobalt. Other materials are referred to as non-magnetic, but they are actually affected by a magnetic field. It's just that the effect is very weak. There are the paramagnetics and the diamagnetics. So a paramagnetic material is weakly attracted to a magnet, but the force of magnetic attraction is very weak and much smaller than the gravitational force, so it's not readily observed. An example would be like aluminum. Diamagnetic materials are actually repelled by a magnet, by a magnetic field. And again, that is a very weak effect compared to the gravitational force, so that's why we don't readily observe it. You have probably played around with magnets and found that materials containing iron, like a nail or a piece of steel, are strongly attracted to the magnet. Whereas there's no apparent attraction between a magnet and a piece of aluminum. Now, aluminum is actually paramagnetic, so it is slightly magnetized, and so there is a slight attraction, but that is not observable because of the strong gravitational force. In fact, the relative permeability for aluminum is 1.000021, whereas the relative permeability for materials such as steel are on the order of 1,000 or even greater. So you can see that it is a very weak effect in aluminum compared to steel. But I want to show you an experiment that will demonstrate that there is a slight magnetization of aluminum when the aluminum is placed in a magnetic field. I have a variable gap magnet here that produces about a half a Tesla magnetic flux density in the center of this gap. That's a very large magnetic field. I have an aluminum rod suspended from a thread so that I eliminate the effects of gravity. Now, aluminum has a relative permeability just slightly greater than 1, so it will be slightly magnetized and attracted to a magnet. So when I place it in this magnetic field, the aluminum rod will rotate so that the length of the rod is in the direction of the magnetic flux density lines going from north to south pole. And if I now take and rotate the magnet, you can see that the aluminum rod will rotate and stay parallel to those magnetic field lines. Also, you can see that the aluminum rod is attracted to one pole or the other depending how I position the magnet. Graphite, which I have a small piece of here, is a diamagnetic material. Okay, so it is weakly repelled by a magnetic field. And I have a thin sheet, and graphite is fairly light. So here's an array of magnets, and if I put the graphite on there, it actually, you can see how it is repelled and actually floats above those magnets. So I can slide this sheet of paper right underneath it. Pencil lead is made out of graphite, so if I bring this magnet close enough, the lead will be repelled. Now, I have found that this does not work with all pencil leads, and I suspect in those cases it's because of too high a concentration of magnetic impurity atoms such as iron. So now we have a glass rod suspended from the thread, and glass is a diamagnetic material. So what will happen when the glass rod enters the high magnetic field is that it's going to rotate, so the axis of the glass rod is perpendicular to the magnetic field. So you can see how the glass rod has rotated so that it's perpendicular to the magnetic field, and so when I remove it from the magnetic field it will go back to its original position. Let me put it in one more time.